Okay, thank you for that introduction. So as the title of my topic suggests, today I'm going to be talking on organ at risk dosimetry and a Monte Carlo investigation investigating how this is affected by penumbra modeling. I have no conflicts of interest and nothing to disclose. For modeling patient dosimetry, modern treatment planning systems will use a multitude of various algorithm types. And through the ACDS audits, we will cover most algorithm types across the level 2 and the level 3 audits using the C-shaped test case, which has been adapted from TG119. So a lot of you will already be familiar with the ACDS level 2 and level 3 audits, but just as a quick refresher, the level 2 audit uses a three-dimensional solid water slab phantom, and the level 3 audit uses an anthropomorphic phantom. Across both of the audit levels, we have a homogeneous and a non-homogeneous with lung case for the C-shaped test case. For the level 2 audit, we use a PTW Octavius 1500 array with a 2D plane of measurement going through two lobes of the PTV and through the OAR. For the level 3 audit, we have 7 IBA CC13 chambers with 6 of them in the PTV volume and 1 of the chambers in the OAR. For the purpose of this talk, we're mostly going to be concerned with these OAR doses. So now, for these OAR local dose variations, what we can do is we can plot them as a national data set, but we can also go one step further and we can separate them out by algorithm type. So starting from right to left, we start off with adaptive convolve, collapsed cone convolution, anisotropic analytical algorithm, Acuros XB, and Monte Carlo. And by doing this, we can demonstrate that different algorithms are better at predicting the measured doses in the OAR compared to other algorithms, and we start to see different biases appearing. What you can also immediately see is that Monte Carlo and Acuros show the most negative bias, being that the TPS is under-predicting the dose. What these two algorithms have in common is that both of them employ what's called an electron cutoff energy for the purpose of computational efficiency. So now we want to investigate why this is the case specifically for the Monte Carlo and the Acuros XB algorithms, and we decided to turn to EGGS-NRC for our own Monte Carlo modeling investigation. Using BEAM-NRC and DOS-XYZ-NRC for the LINAC and the phantom modeling respectively. The reason why we're using Monte Carlo and specifically EGGS-NRC is that it's widely recognized that Monte Carlo algorithms are one of the most accurate methodologies of calculating doses, often referred to as the golden standard. The reason for this is due to its ability to perform and measure radiation transport simulations on a per particle or on a per average particle basis. With EGGS-NRC and Monte Carlo modeling in general, the way that they typically work is that charged particles and photons are transported at discrete steps with randomly generated lengths. And while they're being transported and along those step sizes, different physical phenomena can take place with different probability functions. For example, for MV photons, the biggest probability function is Compton scattering. So as a first step of the investigation, we decided to start off simple and model two AP beams with a central avoidance. And we did so at two different E-cut levels with 10 and 500 keV above rest mass energy. And we took the plane of measurement across the two beams and through the central avoidance structure. And what we find is that in doing so, the higher E-cut energy for the same two fields underdoses in the OAR relative to the lower E-cut energy. So the next step that we needed to do was to compare these differences to two beams of IMRT from AAA and Acuros. And what we find is a very similar pattern in the dose valley, where Acuros, the green series here, is underdosing relative to the AAA recalculation of the same two AP fields. So the only variable in these two simulations is the level of the electron cutoff energy, and this is resulting in a dip in the OAR, or the dose valley. So this makes sense when you remember that the range of the electron can be simplified as being a function of the energy of the electron. So we can demonstrate this visually in a very, very simplified visual demonstration where we're showing that the higher ECOT results in a reduced radiation transport being modeled compared to the lower ECOT. And what results is that electrons with the energy above the rest mass energy but below the ECOT, they can continue to travel, and some of those electrons will travel potentially into an OAR region by crossing voxels. Whereas for the higher ECOT threshold, those same electrons that are above the rest mass energy but below the ECOT level, they will simply have their dose dumped in whatever voxel they are currently in, thus resulting in a slightly lower prediction of the dose using a higher ECOT threshold relative to what's happening in reality. So the next thing to do now is to take the same idea one step further and model an MLC defined C-shape with varying levels of ECOT, or the electron cutoff energy, and I did so using an Electa at 6 MeV. The three ECOT levels I've chosen are 10 keV as the reference, 200 keV, which is what is currently used in Acrios XB, and 500 keV as the maximum, which is also the maximum ECOT what was used in early commercial Monte Carlo and linear Boltzmann solver algorithms, which is what Acrios XB is. The phantom itself is water with 2.5 by 2.5 millimeter voxels in the plane that you're looking at in the XZ, and in the Y direction it's 5 millimeters for improved statistics. And yes, this entire visualization demonstration was done in Excel. Please don't judge me. Okay, so here's proof of the Excel spreadsheet. I can turn on and off beams by interacting with these yellow cells here. And I'm sorry, it's just the most satisfying thing ever. Okay, so now looking at the results, here is the XNRC C-shaped dose distribution. Here is the 500 keV versus 10 keV ECOT, with it being high ECOT versus low ECOT, both of them normalized. And the 200 keV versus the 10 keV ECOT. So you immediately see that it's a much stronger effect for the higher ECOT, which is exactly what you'd expect. For the higher ECOT, it's about an average of 2.2% underdosing in the OAR with a max of 3.1. And for the 200 keV ECOT, it's about an average of 0.5% underdosing with a max close to about 1%. So now we can do the same Acrios versus AAA exercise as we did before for the AP beams, but now we can do it for the C-shapes. So here is an Acrios XB IMRT version of a C-shape, and here is the same IMRT C-shape that has been recalculated with AAA. And when we look at the difference map, we see the same thing that we see across the ACDS national data, where Acrios XB is underrepresenting the dose in the OAR relative to AAA. And now if we compare the difference maps for the Monte Carlo modeling of the ECOT effect and the Acrios versus AAA effect, we see a very similar pattern being displayed in the two difference maps of the Acrios versus AAA and the high ECOT versus the lower ECOT, although it is to a much lower extent in the XNRC simulations. So now to wrap this all up, what we found is that the ACDS audit national data set suggests that there is evidence for variability in the accuracy of different algorithms when it comes to predicting what we measure in our OAR dosimetry. And we've done this by using a Monte Carlo simulation through XNRC, and we found that the ECOT effect on the penumbra modeling can be identified as one potential source of this discrepancy, albeit to a lesser extent. So it does not fully explain why there is such a big difference between the ECOT algorithms and the non-ECOT algorithms, but it does go in the same direction. So to put this all into clinical perspective, when it comes to stereotactic and other small field treatments, you would typically expect that there would be larger penumbra to field ratios, and therefore the penumbra modeling effects on the organs at risk may be significantly more pronounced when OARs, especially when OARs are in proximity to the PTV, as they are in these cases here. But on the other hand, though, the clinical implications may be minimal for the large field treatment, such as prostates. All in all, though, this is probably less of a problem for OARs, not within wraparound PTVs, just to put this all into context. Okay, and now to wrap up my wrap-up, what we have to note here is that this is not a complete explanation. We can't assume that the ACDS measurements in the OARs are perfect because they're not. We're simply going off the data that we have. Having said that, though, what we are seeing is agreement in the ACDS audit organ at risk measurements across two different audit levels. And if you remember back, this means that we're seeing agreement in the OAR measurements between two different detector types in two different phantom types. And what that does is add validity to the audit data and the trends that we're presenting here. So going further, we also have to note that the modeling itself that has been done here has several limitations and it will never be perfect. All in all, though, there is clearly a lot more going on here than simply an ECUT parameter affecting the overall OAR dosimetry. What we do present here is a potential mechanic as to why we're seeing the differences between certain algorithms when it comes to OAR dosimetry in ACDS auditing. Here are some very useful references. Thank you all for taking the time to listen to my talk.